Hello, everyone. Welcome back to the Qiskit Quantum Seminar. I am Maria Villares, and I am your host for today's seminar. I'm doing a PhD in theoretical quantum information science at the University of Oxford, and I also work part-time with the Qiskit community team. With Qiskit, I mainly work with the video team, making videos about resolving quantum paradoxes using quantum computing, and these are all on the Qiskit YouTube channel. And I also help with other video series such as this Quantum Qiskit seminar. I'm delighted to be joined today by Professor Barbara Terhal, who will talk about her research on quantum error correction. We'll wait a few minutes for everyone to arrive before properly starting the seminar and introducing today's speaker. And in the meantime, I'd love to know where you are all joining us from today. So please use the YouTube live chat to tell us where you're joining from. This live chat is open throughout the seminar. Please feel free to drop in questions and comments there for me and Barbara at any time, and I'll pass them on to our speaker during the seminar. I'm joining you from Oxford today, where it's just past 5 p.m. here in the UK. And it's great to see some people putting where they're joining from. We have people joining from India, Ecuador, San Diego, Israel, Iran, lots of different places around the world. More from San Diego and India. Great. Thanks everyone for joining us from so many different places around the world today. So if you haven't already subscribed to the Qiskit YouTube channel, I recommend that you hit the subscribe button. And just as a reminder, this seminar happens every week on a Friday at 12 o'clock Eastern Time. And all of these seminars are recorded, so you can see loads of the past seminars online. But you can only ask questions and join in the discussion when you join us live. So it's really great when you're all tuning in live. And it's great to see people from some more places putting in the chat. We have from New York, Massachusetts. Great. Thanks everyone for joining. So now I'll properly introduce today's speaker, and we can then get started with the seminar. So hello to everyone that's just joined us. I'm your host, Maria Villares from the Qiskit community team and the University of Oxford. And I'm joined today by Professor Barbara Terhal. Barbara Terhal is a Dutch theorist working in quantum information theory since her PhD in 1999. She was a visitor, then a postdoc, and then a research staff member at IBM Watson in Yorktown Heights until 2010, working on topics such as entanglement witnesses, the power of constant depth circuits, quantum complexity theory, and quantum error correction and fault tolerance. So it's great to have you back connected with IBM. And in 2010, Barbara left IBM to become a professor in theoretical physics at the Technical University in Aachen, and then she moved to Delft University of Technology in 2017. She's been a fellow of the American Physical Society since 2007 and a distinguished visiting research chair at the Perimeter Institute since 2014, and a fellow of the Royal Netherlands Academy of Arts and Sciences since 2020. So thanks, Barbara, for making the time to share your research with us today. Could you tell us where you're joining us from today?
Yeah, hi. Nice to join the seminar and be allowed to speak here. I'm joining from my home in the south of the Netherlands, and it's 6 o'clock here, so in the evening.
Great, thanks for joining us for this evening talk. And yeah, I'm looking forward to hearing your talk, and I'll hand over to you now. And everyone, just as a reminder, please feel free to post your questions in the chat, and I'll try and feed them into Barbara during the talk. So yeah, over to you, and thanks.
Okay, thank you for the introduction. Yeah, so I'll be talking about some error correction that I've been interested in, and it's error correction very directly related to superconducting circuits, as IBM makes them and other teams make them. But it's not focused on the qubit that IBM uses, the transmon qubit, but it's focused on a different type of qubit, which is called a 0-pi qubit. And it aims at interpreting some of the known circuits, electrical circuits, to make these qubits as certain codes, and we call them homological rotor codes. And I want to explain a little bit about this connection in this talk. And my talk is basically based on a paper you see here at the bottom by my colleagues Christophe Viau and Alessandro Chiani, that's going to appear in Communications in Mathematical Physics. So as you can see from that sort of journal reference, this may be a slightly mathematical talk, but the interesting thing is that I think it's slightly mathematical, but then it also comes to sort of topics of electrical engineering. So it crosses several fields, I hope. All right, so let me start. So as you may know, the transmon qubit is not really a qubit. It's sort of an anharmonic oscillator. There are more than 2 levels, energy levels, and that causes some trouble. It causes leakage. And, it's maybe interesting to say, well, maybe we should try to build qubits in sort of more in the native Hilbert spaces that we have. And by native, I mean that maybe we have a resonator, some cavity, or some coplanar resonator, or we have a superconducting island, and those degrees of freedoms are not natively qubits, but they are oscillators and rotors. And so the idea is, and this is not a new idea, I think somebody like Kitaev worked on this for a long time, maybe we can come up with ideas for hardware protected qubits. So qubits that are matched well with the hardware, and that somehow, because the way we design the sort of the qubit subspace, there's protection against noise. And in this case, this is sort of categorized as charge and flux noise. All right, so I mentioned the word rotor. Now, maybe you already have some idea about this, but let me just be a little bit more formal about this. So what is a rotor? So a single rotor, the way I think about it, is just a Hilbert space that can take values, the basis vectors can take values in Z. So it can be any integer. And the way I can physically think about this rotor, that integer could be angular momentum. It could be represented by the number of, Cooper pairs on a superconducting island. So there's sort of an excess number of Cooper pairs with respect to some reference reservoir. And so this number could take values going from minus infinity to plus infinity. But of course, the minus infinity plus infinity is a bit of a fiction. So of course, there will be some finite Hilbert space available, but the boundaries of this are not as clear. It's not, you can't say, oh, this is a qudit with dimension, 10 or something. All right, so with that variable, you can also just go, do a Fourier transform. So you can go to a different basis, and then what you get is a phase variable. So that I denote with theta. So L and theta are the sort of important sort of operators and variables that I work with in this talk. Now, in that Hilbert space, I can also define generalized Pauli operators, Pauli X and Pauli Z, and these also will play a prominent role. So let me give their definition properly. So generalized Pauli X, you can see here, and there's not just one operator, as you may expect. There's an operator that's labeled by an integer m. And so if you see what it does, if you act on it on a state with, say, a certain number of charges, it increases this charge, the number of charges, by m if I apply xm. And so if you're familiar with superconducting circuits, there is actually a very normal element that's used all over the place, which is the Josephson junction, which can be written in terms of these operators. Basically, what the Josephson junction does in terms of the interaction in the Hamiltonian that it represents, it is the cosine of these two operators corresponding to two islands. And what it physically represents is that one Cooper pair moves from tunnels from island 1 to island 2. So we diminish a charge here and we add a charge on the other island. All right, so that's generalized poly X, but so let me talk about poly Z. And so again, I define some operator, you see it here, and now this again is exponentiated and it uses the operator L. And what it does on a state with a certain phase, it shifts the phase. So that it causes phase fluctuations, and it is generated by an operator. If I see L as a charge operator, if I have that term in the Hamiltonian and I don't want it, it's sort of representing charge noise, which causes these phase fluctuations. Now, this rotor, one of the important things which makes it sort of interesting is that, these two conjugate variables that are, for an oscillator are, take values in R. Here, one takes values among the integers, and the other one is continuous, but in a finite interval, 0 to pi. Right? So they play different roles. And that different roles you can also see because we want to define basically a stabilizer code using multiple rotors. This is what my rotor codes are about. And for stabilizer codes, what we do is we have to construct parity checks. So we take, poly Z's, and then we take products of them and say their eigenvalue has to be set to 1. So in this case, for example, we take 4 rotors, and we say the eigenvalue has to be set to 1, but it has to be true for any value of this angle. And this is an important thing because this angle is continuous. And when this has to be true for any phi, then it basically means that the sum of these charges on the 4 islands or on these 4 rotors should be 0. So I just showed you that these terms, like let me just go back a slide, terms involve these operators X, sometimes relate to Josephson junctions, and terms that relate to the poly Z, in this generalized poly Z, they relate to charge terms. So they come about as capacitive constraints. And in addition, you have some commutation relations between, these two generalized poly operators, as you'd expect, and you have some multi-rotor extension. All right, so now let's pause for a moment because I'm saying I'm going to define rotor codes using the stabilizer formalism, using my generalized poly X's and Z. But why is this interesting? And I want to make that point before I do a formal definition. Now we get very normal, nice codes by a homological construction for qubits. And the way this goes is we take a surface with non-trivial topology, like a torus, and we tessellate it. So we make it discrete, and then on every edge we put a qubit. And what we do then is we associate with the vertices of the lattice Z checks, with the faces we associate X checks, and that is what we call the toric code. So if you haven't seen the toric code before, it maybe goes too fast, but if you have seen it, I'm sure you recognize this thing. So then a very natural question is, what if I put, instead of qubits on all these edges in this figure here, I put rotors there, and I define my checks now with the generalized polys. What do I get? Well, basically, instead of encoding 2 logical qubits, I encode 2 logical rotors. Okay, so maybe that's not extremely interesting, because in the end, we want to use many rotors to actually encode qubits. So that's what our goal is. We want to encode a logical qubit using rotors. So natively, our hardware mainly uses rotors, and in the end, we want to end up with qubits because we want to do computation on qubits. And the answer, and basically this is one of sort of the realizations or the results that we had, is that it's a mathematical fact, but we realized that it's useful, that when you tessellate a manifold with torsion, sort of a twistedness, we'll see an example, then you can actually encode a qubit in 2 dimensions. And you actually, in 2 dimensions, you only encode a qubit, you only encode 3 qubits or a qtrit. You encode a qubit due to, if you tessellate a 2-dimensional manifold. All right, so let's see how this works out. Now, first, I have to define the stabilizer. And here looks like kind of a complicated mathematical formalism. So let's sort of unpack this. Now, if you're familiar with stabilizer codes, you know that there are parity check matrices. These are binary matrices, and you have one for the X checks and one for the Z checks. And here, these matrices I call HX and HZ. And instead of being binary matrices, these are matrices that have entries in Z in the most general case. We will actually be sort of constraining ourselves to codes where these entries are just +1, -1, or 0. And the rows of these matrices have to be orthogonal. Okay, so I got those matrices that have that property, and from that I build a stabilizer code. I basically use these matrices now to have X checks and Z checks, and the important point is that every Z check comes with this continuous angle phi, right? All right, so maybe let's look at that, how this works out in a small example. And here I'm tessellating the real projective plane. And what is the real projective plane? Well, it's just a face, it's a plane, but on the boundaries, I have to do something special. I don't put periodic boundaries like I do on a torus. No, I have to do them in twisted fashion. So if you look at this, just a picture from Wikipedia. If you look at this boundary, if I'm at this point, I should identify that with this point. And this point should be identified with that point. That's the real projective plane. And now I can make a tessellation of that real projective plane is this figure. So what are we seeing here? So we have to imagine that, I have edges, and on every edge, I have a rotor degree of freedom. So I have 4 edges here, because if I'm on this edge actually continues here, same edge. And so you see it sort of, goes around. And similarly here, this edge too continues there. And there is an orientation that I actually do really care about. Let's say if I'm traveling on this edge too, I go out here and I come back there. And here, if I'm going out here, I come back there. So this is sort of how you see this twistedness. Okay, so now what do I have in terms of faces? So I have a face here that involves, edges 3 and 4. I have a face here, which is sort of twisted because I come out here and then I go around here and then I'm actually over here. Right? And this is again a face that involves only 2 edges. And then I have a face that involves all 4 edges. And these faces, these 3 possible faces, are kind of the parity check that I associate with it. There are 3 rows associated with these faces. And then I also have 2 vertices, this vertex, the black one, and the other black one. And for every vertex, I look at the edges that come in. There are 4 edges coming in. And I associate, they have support on all the edges that are coming in, and the sign is determined by whether these edges are incoming or outgoing. Okay, you see, and this is actually, these 2 constraints are equivalent. All right, so these are hx and hz, but now to get the stabilizer, I put things in the exponent. So this type of check gets translated into what I have here. And here you see, hey, this is sort of a constraint that says that the sum of L1, L2, L3, L4 must be 0 to be in the stabilizer subspace, so to say. And these constraints say other things. So, I have something like this, something like this, something like this. All right, so now we want to think about, and this is really the crucial point about rotor codes that allow you, enable you to understand why I'm encoding a qubit. We can compare this code with what happens when we put qubits on the edges or when we put oscillators on the edges. All right, so let's go back to qubits for a moment. So what we know about qubits, that these signs don't matter. So I just have, -1 is just +1. And then you see that the third row is just, linear independent of the first 2. I don't need to include it. And the code I'm actually having here is just the smallest possible surface code with some XX checks, XX and XX, and a weight 4 ZZ check. That encodes a single qubit, right? So if I do it with qubits, I code a single qubit. Now, what if I do it with oscillators? Now, with oscillators, I do care about the signs. And then you ask and say, you look at these signs and you say, hey, I'm in a 4-dimensional space. I have 3 vectors here. So there's only 1 vector that's orthogonal to it, which would be the candidate logical Z. But that vector is actually a stabilizer. So with oscillators, I don't encode anything because these signs matter, and I'm looking for a vector that's orthogonal to these 3 vectors, and there is none. And so the trick with rotors is that you actually can encode a logical qubit. There is a little bit of sort of encoding space, but it's not because I make a vector that's orthogonal to this, but I do something that is sort of clever. All right, so the way we can see this is the following. You can say, okay, I'm going to look for some operator that is a sort of a Z-like operator that commutes with this. And if we look at this thing, so if you see here, these 2 operators commute. Why do they commute? Because, there is some commutation due to theta 3 with L3, and there's some commutation theta 4 with L4, but the signs are just different, and so these cancel. And so the total commutation, in totally they commute. All right, fine, but now there's something else I can do. What if I take this angle to be pi? So if I take the angle to be pi, the commutator, the product of these, essentially there is an e to the I 2 pi difference. So because e to the I 2 pi is identity, these operators also commute. Okay, so the point is that only for when this angle is pi do I have this commutation relation. This is the crucial step. And this operator with the pi phase shift on a rotor number 3 and rotor number 2, that is the logical Z. So that's shown in blue here. So for these rotor codes, what you do is always a pi phase shift on a bunch of rotors. That's why maybe it relates exactly to the 0 pi qubits, of course. Okay, and then there's also a logical X that I can associate with it. And these two operators have weight too. All right, so that gives you, if you don't know what torsion is, it gives you a little bit of an idea what is sort of, what's the sort of window of opportunity that's used here by these rotor codes. Okay, we can be more mathematical, and for these tessellations of surfaces on which we put, degrees of freedom on edges, we actually care about the first homology group of the cell complex that we obtain. And the point is that when you do that over Z, and the Hilbert space is, has labels in Z, then we can have torsion. These groups can have torsion, and this is not true for oscillators and qubits. And so this is a mathematical way of saying essentially the same. And so for 2D surfaces, like for example the Moebius-strip, which is non-orientable and which therefore has torsion, I can encode only a qubit. If I go to higher dimensions, I can also have manifolds with torsion, but there's not necessarily a relation with orientability, and I can encode all kinds of things. You can look at our paper for other sort of code constructions. All right, so now what I want to discuss, so maybe in the last slide, we saw a Mobius-strip. So I can tessellate a Mobius-strip, all right? I can make it out of little squares, and the way I'm going to do it, so I can take the strip, and at the end, I have to have a twist. Right, and I put, like the surface code or the toric code, I put squares on it, and there's sort of what we call a rough boundary at the top and another rough boundary at the bottom. So these boundaries, the top and the bottom, are not connected because it's a Möbius strip, and the twist is over here. All right, if I analyze that code, it turns out that the logical Z is pi phase shift on all these red edges. And if I make this strip very long, like say this is, length n, so this looks like this has a high distance scaling with n. And also the logical X is something that goes down from sort of top, to bottom. And if I make that also long, like n, the X distance is also proportional to n. Now, I want to say more about the distance, and I'll do that in a moment, because you can ask, is the distance really growing like n for this code? But before I do that, I want to just briefly introduce a sort of a very thin Mobius strip, because instead of having some thickness in this, in this non-twisted direction, we can make it as thin as we want. And the thinnest version is essentially this thing. So the thickness is 2 rotors. Basically, there's a rotor on this edge and there's a rotor on the bottom edge. And what you see is that the check that lives at the vertex now involves 2 rotors. That is particularly nice and simple. There is also a check that lives, is a phase check that involves 4 rotors, like this one, this one, this one, and this one. And in math, this is given over here, but you don't need to check it necessarily. We'll come back to this thin Mobius strip in a moment, because one of the known 0 pi qubits can be identified exactly with this rotor code. But for this rotor code, you see that because this is very thin, this X distance is very small, it's 2, and the Z distance, grows with n, so it's sort of long. Okay, so now coming back to distance. So, why do we care about distance? Well, we care about distance because we really care about the probability that logical errors happen. That is the more fundamental question. But the probability that logical errors happen depends on my error model. So I have to say, well, what's the probability for, say, xm on a single rotor? Now, it's kind of natural, like m is the number of Cooper pair jumps, say, number of charges that changes. So, that could scale like p to the m. That's kind of a natural model for some probability p. Now, I could also look at the probability for z of phi. And remember, phi is, continuous. So it's natural to say that this is, some Gaussian distribution. And it's important to note that this goes like phi squared. It seems kind of obvious, but it will become important. Okay, and then I say, okay, let me say now I have some logical operator. Maybe these are, pi phase shift on this whole strip. And I can ask, what's the probability for doing that? And I take minus log of that probability. And if this involves, n rotors, then this minus log probability will scale like n. Okay, but now, as you know from stabilizer code characterization, there are other ways to do logical operators. I can deform these logical operators. And for these codes, because the Z stabilizers have continuous parameters, I can continuously deform them. I can sort of, tide over a little bit of this pi shift on neighboring edges and make this less of a pi phase shift. And that is shown sort of extremely in this figure, because what I do, so basically I have my logical Z that has pi shift on a line, but what I can do is I can spread out the support, and I can spread it all the way along this width. And this is not so easy to see that you can do this, but we've worked this out carefully, that instead of having a pi phase shift along here, you can have pi over 5 phase shifts, plus or minus signs, on all these yellow edges. And then along this twist, you have some slightly bigger phase shift. But the point is that it may be much, more likely to have many small phase shifts than a smaller subset of larger phase shifts. And why is that more likely? Is because if the phase shift, goes down with 1 over W, which W is the width of the strip, then the probability for it will go, over the log, the probability will go down like 1 over W squared, right? Because of the square in the Gaussian. So this is basically the argument we give. If we have a W times n lattice, so the width of the Mobius strip is W, then we can make a logical Z that has, for which our definition of distance scales like n over W. And this is not so good, right? Because we like to make W longer because we want a large x distance. But we can't win both ways. We would have to make n scale like W squared in order to get a Z distance grows with n still. So you could say, well, but a strip where the one is distance is n squared and the other one is n is effectively 1D. And we believe this is a very fundamental point in that, you're familiar maybe with the Torah code and the surface code being a good memory in 2 dimensions. And you can ask about decoding this. And, the larger the lattice grows, the more stable it becomes if you're below the phase transition. We believe that for this type of code, if we do active error correction, let's say we measure these stabilizers, there will not be some phase transition from a disorder to order phase, but there will be more something like a Kosterlitz-Saulus transition, as people have studied in 2 dimension. So we don't fully know the details of this, but we actually can map the decoding for a model like this onto a so-called 2-dimensional XY model, which is known to undergo a Kosterlitz-Saulus phase transition. And this probably has consequences for the ability to store information in this sort of logical qubit in some manner. So in some sense, 2D is too low dimensional to actually for reliable storage if we start with these rotor degrees of freedom. Okay, so let me see how am I doing on time. I think I'm doing okay. So now I want to sort of focus a little bit more on what I announced at the beginning of my talk, that I would relate this to circuits for 0 pi qubits. And I've already alluded a little bit to this thing that maybe we'll need some Josephson junctions and we need some charging terms. And let's look a little bit more how this come about. Okay, so what we want. So in order to make contact with the known qubits, these qubits are given as a Hamiltonian of an electrical circuit. So we can say we would like to build the code Hamiltonian. And the code Hamiltonian would be something where the ground space or any eigenspaces of this code Hamiltonian are doubly degenerate, and that double degeneracy represents my qubit. Now, you can do this for stabilizer codes, so qubits, and then you have a Hamiltonian that has so-called topological order, and it has gaps and so on, at constant gaps. And so you can look at then at the stability under perturbations, and you can argue that qubits encoded in this Hamiltonian have a certain stability or protection. This here again is more subtle because this Hamiltonian that I'll construct is gapless because I have a sort of continuous parameter, and so if there are continuous fluctuations, then I'll be continuous. So there's something that is different here. All right, but let's beyond that, let me just say a few more things about engineering this code Hamiltonian. So what I want, if I had sort of a code, say the general code with a matrix HX and a matrix HZ, and the HX has rows and they're called HJX, so that's one of these rows out of these parity check matrices, then I'd like to engineer a term BX. And this is a sum over all the rows. And for every row, I get some cosine of phases of multiple rotors. And none of these, not necessarily are these terms easy to analyze. And, in some cases, we know how to do this. But these are, you could say, inductive constraints because they're coupled to the phase operator. And similarly, for every, I have the HZ is the other matrix, and it has rows as well. And I like to build some terms like this, because these terms, if I want to be at low energy, I'll have to, this has to be 0. And if this is 0, this is some linear combination of, charge operators of a bunch of these rotors, then I'm in the code space. Now, engineering this code Hamiltonian is one way to go. Another way to go, which has not been researched at all, is to come up with ways to measure these checks explicitly. Right, so you have other degrees of freedom, detecting sort of a current or a charge or measuring a charge, and we haven't really worked this out. Okay, so this is a very general thing, but it doesn't necessarily seem very easy how you actually build these types of terms with an electric circuit. Now, there is one thing that you can say about the capacitive terms. And at least there's some way of we can do some types of terms pretty easily. If we have terms that are the sum of these L's of a bunch of islands. So let me just go back for a moment to one of these types terms. So it's over here. So here I have the sum of L1, L2, L3, L4. So all come with a plus sign. So it says the total charge here has to be 0. These types of terms are sort of not too sort of complicated to make, at least intuitively. So if you're familiar with electric circuits and how you build a Hamiltonian on it, it kind of goes like this. So imagine we have some network of superconducting islands, and each one of them is connected to ground via sufficiently large capacitance CG. And if we just look at what that capacitance CG does, is that when it's sufficiently large, then, charge fluctuations on the islands don't cost a lot of energy. I can add a charge, fine, it's a large capacitor. And so that's kind of captured by this term. Okay, that's fine. And we like that because we'd like to allow, of course, in every island, there should be a sufficiently large Hilbert space. Okay, maybe not running from minus infinity to infinity, but sufficiently large to really build a code. Okay, but now we want to implement this sort of a capacitive term. So we imagine, say, a cluster maybe of 4 nodes or of 2 nodes, and between those 2 nodes, we put a much stronger capacitance. And essentially, we allow, charge differences between nodes there. And so it's only the sum of the charges of those 2 nodes, which has to be, low, say. And so, if you sort of do the math, then what you get is you change the Hamiltonian to something where in this cluster, let's say there are two nodes, you just get some term like this. And other terms that are sort of, corrections to this, they are of order CG divided by C. And so if C is much larger than CG, they sort of can be neglected, right? And so the point is that this type of terms can be viewed as some kind of X-check, which says that the sum of these charges in this cluster, and maybe I have multiple clusters like that, has to be 0. Okay, so that works sort of okay. So now the essential point is I have to explain to you, how you do cosine of, some sum and difference of these, theta operators. Now, in general, that's not so easy, but actually this problem has already been solved, maybe not so surprisingly, by Kitaev and other workers. There's a very nice paper by Weiss et al. In which they analyzed this Kitaev, what is called current mirror qubit, or 0 or pi qubit. And that picture, in their paper, you can see this picture. And it's the way you get this type of term from Josephson junctions and some capacitors is perturbatively, essentially. So we imagine a circuit here on the left. So we have 4 nodes, each characterized by some theta, and each capacitively coupled to a ground node via some CG. And then besides the CG, I have 2 capacitors, or I have a capacitive coupling C that, as I mentioned before, is much larger than CG. So this is sort of one cluster, and that's another cluster. And then there is a Josephson tunneling junction between, over here and one over there. And there's also some capacitance that goes with that, but let's neglect this. And the idea is as follows. So a Josephson junction, what can happen is a charge can tunnel, right? Let's say I'm in the space where I have the total charge on these, theta 1 and theta 3 on these 2 nodes is 0. So a positive charge here and negative charge there. Now this charge, this Cooper pair, can tunnel, right? But in order to remain in a space where, the total charge is 0, the other charge also likes to tunnel, right? So the negative charge also tunnels here, and we're in this configuration. So this is sort of a joint tunneling process, and this is exactly modeled in the Hamiltonian by this type of term, this joint tunneling, right? So if we want to remain in this space where I have, the sum of charges here and the sum of charges here is 0, then the effect of the Josephson junction is to tunnel twice. Huh? And so you can analyze this with some perturbation theory, Schrieffer-Wolff, and so on. And that's what they've done in this paper. And it generates this type of term, which is exactly the type of term that we may want for a code. Right? And so basically, if we want to understand this Kitaev current mirror qubit, which is also referred to as the Moebius-strip qubit, there's no surprise here, we're basically there. So I had, in my rotor code, I had this picture where I said every edge is a rotor, and I have 2 rotors on top of each other. Okay, so here are the nodes corresponding to a rotor degree freedom. These are just, every one of these is a superconducting island with this degree of freedom L and theta as its fundamental degrees of freedom. Then so these constraints, these vertex, so I have constraints that say that the sum of the charges here should be 0, and that is kind of enforced by these capacitors. And then what is very nice about this thing, I have, these phases correspond to these cosines of the 4 phases. And these can be realized in the subspace in which these vertex constraints are also satisfied. So that is done by these Josephson junctions. And then at the end, I need to do a twist because this Moebius-strip has a twist, go like this, and then I come out here. And that twist happens all because this is connected to that. And this is not connected to the top ladder, to the top thing, but to the bottom. All right, so now I can also, the logical Z. So now I can kind of try to understand what the protection of this qubit is from this code perspective, because that's, I think, the usefulness of this code perspective, that it gives us a way of understanding what we should be expecting when we design this qubit. And so indeed, so if you realize that the logical Z is increasing with n, then, and it's actually something, that is, so it takes sort of the pi phase shift along the whole ladder, then you kind of understand that the phasing time will, is increasing with the number of rotors on this ladder, the longer this strip becomes. And that is sort of capturing this charge noise protection. Now, the actual story is a little bit more subtle because I can also have excitations, gapless excitations above the qubit space. And through these gapless excitations, I can actually sort of, make a logical Z error. And it is not so clear, whether this will give protection scaling with n. I believe rather that this would be sort of order 1. The other, sort of logical X, as I argued, this only has distance 2. And so that limits my T1 essentially, but the associated sort of noise source is flux noise. Now, if you're familiar with analysis of T1 and T5 in these qubits, then having this code perspective is sort of rather different and maybe slightly confusing, because actually Weiss et al. Has slightly different conclusions than what we say in our paper. But of course, we believe that because, the logical operators of our beautiful qubits, or our sort of ideal qubits, Z only involves the operator L and X only involves the operator theta. But in practice, because the qubit is imperfectly realized, the logical Z may actually involve both operators. So you can look at the, how T5 is sensitive to charge noise and flux noise. And so that's what's more done, for these qubits. All right, so now I want to talk about the last, so there are sort of 2 circuits that have been proposed sort of as 0 pi qubits. And the other circuit, let's look at that. So this is the circuit for the 0 pi qubit. It's a smaller circuit. It's not something that scales with n. So it's, okay, there's the phone going off here, but I'll ignore it now. So this circuit uses inductors, and we want to pause a little moment to say what these inductors, what the role is that they play. So if I remove the inductors from the circuit, it just sort of looks exactly like this 4-phase gadget. And I'm again in the regime where C is much larger than some, capacitors to ground, which are not shown here. And the Josephson junction is kind of weak, and I can perturbatively analyze it. But this circuit, if I have no inductors, would have 4 nodes, and it's not quite clear what code it would correspond to. And we claim that, we can interpret this circuit as a code, which is actually also a tessellation of the real projective plane, but only with 2 degrees of freedom. So let's look for a moment at this picture here on the right. So what this is like, I have 2 rotors, number 1 on this edge and number 3 on this edge that continues along on the other side. It's extremely simple because then I just have, 1 capacitive constraint connecting 1 and 3. So that's noted by this term. And I have 1 face, but it's kind of a funny face because the face touches this edge 1 coming through here, but then this face actually also has to wrap over to the other side, and it touches the edge 1 again. And the same with the edge 3. So there is a 2 here. Remember the rotor codes, the matrices that I have, the parity check matrix could come with integer entries, not just +1 or -1 or 0. And if they come with an integer 2, then I'll have a 2 in this cosine. And essentially, if you look now at, so if I take out the inductors, I have sort of like a 4-phase gadget, and I'll get a term in the Hamiltonian that looks like this. That's because of this tunneling of pairs, of Cooper pairs, basically. And now what the inductor does, it essentially identifies degrees of freedom. It identifies theta 1 with theta 4 and theta 2 with theta 3. And this is sort of a subtle thing, but let's look for a moment. If it identifies theta 1 with theta 4 and theta 2 with 3, then I do get something like, this factor of 2. And I get the observation that this potential has minima at 0 and pi, hence the name 0 pi qubit, because one state of the qubit is localized, is a wave function localized at 0. The other one is a state localized at pi. All right, but why do the inductors allow me to identify the degrees of freedom? If I could identify the degree of freedom, then maybe, if the inductor is so strong, then I should be just, looking at a different circuit, because theta 1 is just equal to theta 4. And then if I look at that circuit, I actually won't do this analysis. So actually, this inductor has the scale of the strength of an inductor has to be chosen in a sort of subtle way, because there are several energy scales. So the way we can look at an inductor is it can act as a short circuit at low frequency, meaning that this term is really small, because frequency is low, omega is small. This is the impedance of the inductor. And we want to be working in the low energy space set by these capacitive constraints. And in that space, we want it to act as a short circuit. A short circuit means that I can identify the nodes, and I get my effective cosine 2 theta 1 minus 3 coupling. But at higher frequency, I want it to be an open circuit, because I don't really want to identify these nodes all the time. And so this sets sort of intermediate energy scales that, how EL, varies for the, the difference between EL and the energy scale set by C, and the difference between EL and the energy scale set by CG. Okay, so this is a subtle regime. I don't think, we have much to add on the insights on this qubit, and you could see this as a small code qubit. Of course, no distance is scaling with n here, but maybe there is some, built-in protection due to seeing this as a qubit. All right, so now I want to wrap up. Let's see, am I doing time? Okay, fine. So, basically, what are we interested in still? What we would like to understand a little bit better is how we make a Mobius-strip code with a larger width. You've seen that this Kitaev circuit, this Mobius-strip circuit, or the current mirror qubit, is a thin Mobius-strip, and we'd like to make a thicker Mobius-strip. For that, we have to deal with the capacitive and the inductive constraints in a more complicated way that probably require us to use inductors and analyze, do more extensive analysis. So this is work in progress. Another question that you can ask yourself, and that we didn't address in our paper, but fortunately has been looked at very recently. So this is a few days ago, work by Xu, Wang, and Albert, on what are the Clifford operations for these codes, because there's sort of, because we have phase and integers, so, something in 0 to pi, the interval 0 to pi, and integers, some of the symmetry between P and Q or in X and Z has been broken, right? They figure out some of these aspects. So I think that's quite an interesting paper, because, in building this, in doing this work, we were not sort of aiming at sort of making a competitor qubit for the transmon qubit, because, we don't even know how to operate on. We don't have such good, candidates for this qubit. So there's still a long way to go, but we see it as, fundamentally sort of interesting to explore this. And to end now, I'd like to throw out one thing that we found kind of neat, because I've sketched this argument, and in 2D, we are not really getting, a topological phase of matter, so to say, right? Which you would get with qubits, and that's because there is a continuous degree of freedom, and, it's known in physics, there are, Merman-Wagner theorem and things like that, that in 2 dimensions, continuous fluctuations destroy order. And I would see this as a remnant, or, another sort of, demonstration of these ideas. So we need to go to 3 dimensions. And so you can actually make a 3-dimensional code, so you can tessellate, a 3-dimensional volume. And again, you have to make the boundaries sort of twisted. And so here, for example, here on the right, we have a figure of that. We have rotors again on edges. So if you know the 3-dimensional Torah code, you know that you can put the qubits on edges. So here you put the rotors on edges. You have phase checks, which are weight 4, which again are these cosines of 4 phases. So there's sort of joint tunneling of made from Josephson junctions. And you have capacitive checks that involve 6 edges. But then in addition, you need to make, you need to identify nodes on the outside in this sort of, this guy here, over here has to be identified with that. So it requires some long range, edges, and these translate in that, in terms of hardware, you have to make superconducting islands that stretch from here to over there. I haven't really given that much thought because I don't know any structure that's made in 3D, a bulk, structure that you make in 3D. So this is sort of for the future, but we believe that this could be a genuine new superconducting phase of matter, right? We don't just store, there's not a stable superconducting phase. No, we actually have a real qubit degree of freedom that's being sort of held stable. Okay, this is, I think, what I'd like to leave it at. I don't know whether there have been any questions so far, but this is my last slide.
Great, thanks. Thanks for the great talk. Yeah, it's really cool to see the combination of the kind of abstract mathematical aspects and then how we actually think about implementing these experimentally. So yeah, we've had some questions coming in. I didn't want to interrupt the flow of your talk, so I saved them until now. We have a kind of clarificatory question about the beginning, the diagrams at the beginning. So the question is, does Hz correspond to vertices and Hx correspond to faces?
Yeah, so let's go back to one of the earlier slides. So the X checks indeed are, okay, so I think, yeah, so maybe it's this slide that the question was about. So the Z checks indeed correspond to vertices, and the X check correspond to faces, which I know, sometimes for the surface code, it's quite the opposite, but of course, it doesn't matter what we call X and Z, it's just a convention. Yeah.
Mm-hmm. Thanks. Another question is about if there are advantages of using 10-dimensional qudits.
Not that I know of. I think, I think I see this project more as it's just, we're physicists. We're not only sort of aiming at building quantum computers, we're just aiming at building different matter, that it's behaving in new ways and that we understand the mathematical underpinnings of. And I think, why not a 10-dimensional qubit in that sense? Although the point is, of course, we try to make, by focusing on these codes that are tessellations of a 2-dimensional manifold and maybe 3, we try to focus on things that are actually physically realizable, right? And maybe other people have ideas about where, angular momentum operators that can take sufficient number of values would be an interesting, degree of freedom to use. So we've identified them as superconducting qubits, but there are other, maybe, large spins or something. There may be other platforms in which you can think about rotor codes.
Cool. So superconductors are the kind of natural hardware to think of, but it could also apply to other. I haven't given this too much thought because we realized then that the 0 pi qubits are kind of, versions of these codes, and that you have this Josephson junction, so some of these sort of operators you get come out sort of naturally. But yeah, I don't know, maybe there, why not think about other implementations with real rotors, mechanical rotors, I mean. Yeah. Cool, thanks. Another question is, do you have an intuition on what the threshold error rates might be for some of the small homological rotor code examples presented? And how do you expect they compare to topological qubit codes on qubits?
All right, good question. Yeah, so the point is that, okay, so you say threshold, but we're not even sure there is a threshold. Well, of course, there is a question, okay, so it's a threshold for a small code. You can just say, well, okay, I just look at I have some native error model, and then I just look at the probability for logical errors, and if that's lower than the probability for elementary errors, I'm below threshold. And we haven't looked at this question. I think so. You mean this threshold may vanish when I go to large code size, but it could be non-zero for a small code. It's just some value. We haven't looked at this question because also we have to first define, okay, we measure these checks, you can define that, and maybe we measure them with some error, but then you have to also think about a decoder. And well, we wanted to do this, but we haven't had the time to do it, basically. I think the decoding problem is not as easy as it is for the surface code. Of course, the surface code is lucky that it's sort of, there's an efficient decoder for it. So it hinges on that question as well. But it's a good question to try to, how would you decode this, how you set it up.
Mm-hmm. Interesting, cool. And another question is, how many physical qubits will be required to encode one logical qubit?
Yeah, so, well, I never start with physical qubits, right? I start with rotors. So you could say, well, a single transmon qubit is actually a rotor. And so you can say how many transmon qubits. So here in this example, on every edge, I have a rotor. So I have 4 rotors, and then I encode something. But this scaling, the scaling of, how many, well, the distance. Okay, so the naive distance scaling that you have for these codes is similar as the surface code. So it's not very efficient. So you can also define LDPC codes and, can do everything for rotors. I mean, we have some sort of, I think in our paper, we have something about hypergraph product codes also. But the problem is that the distance, usually with qubits, you think about, okay, the distance is just, okay, I do a logical, what's the least number of qubits that it can act on? And that's the distance. Okay, done. But my point has been that to say that's not the distance, that's not the proper distance of these codes. Because the distance is really motivated. Why do we say the distance is the minimum number of qubits that a logical acts on? It's because this is the way to do a logical with a minimum probability of error. But if I have a model where it's extremely likely that the phase of every rotor just is slightly jittering, right? Then I can make small errors very likely. And if I can, the point is I have this spreading out of this logical operator. Sorry, just this problem. Okay, so this is an issue also for if I have an LDPC rotor code, at least I have to argue about what the distance is. It's slightly different. Does that answer your question? I hope that you can't answer back, of course, but I hope it answers the question.
Yeah, thanks. And if anyone else wants to drop in a question, we could respond to that as well. So feel free to drop in another question if you have one. Thanks for everyone who has been asking questions so far. And I guess as a general kind of high-level question, what so you mentioned some things to think about, for example, the efficient decoding and so on. What do you think are the most interesting next steps to think about with developing this project?
Yeah, well, I think this, I've mentioned that we believe this has in these 2D codes, there's no sort of memory phase, or it's different. And I'd like to understand that a little bit better in principle. So for that, there's a way of mapping the decoding problem onto a StatMech model, which you can do for the Tor code. And then you get a random bond Ising model, and you can do this here, and then you can sort of random XY model and so on. And if you had a decoder, then you could actually study this numerically a bit more, and also connect more directly this Koszalik-Tsoulis phase transition to what happens with the logical error rate, because we believe that there's some work to be done there essentially to make this a little bit more clear. There's also this thing about, if you say I measure the stabilizer checks as we do for the surface code, or imagine doing, I have no idea how to do this here. Because I think I mentioned on the slide, you measure a current or a charge, but there's no proposals of how to do this. So that's slightly different way of operating such a qubit. Not building a code Hamiltonian, you're doing active error correction. Yeah, but I think one of the things that maybe I hope to see, I mean, I know these 0 pi qubits have not been, some people have experimentally made some 0 pi qubit. This Kitaev's current mirror qubit has not been made. And I hope maybe this type of work stimulates some experimental work in these directions. Although, of course, this is not going to build as a quantum computer, right? It's more of a physics interested question, basically. What I mean to say is that, like, it's hard to compete with a transmon qubit, and you sort of make some kind of very fancy qubit. It's, but it's worthwhile, I think, doing. Yeah. But of course, I don't do experiments, so.
Yeah, cool. Yeah, I think that kind of relates to another question which has come in. Which is asked about what is the closest near-term application.
Yeah, I don't see a near-term. Well, I mean, if your application solve, the world's hunger problem or whatever, I don't see applications in the sense that I find it just fascinating that I think it's important to learn how. Okay, so if you know about the Tor code, you say, of course, 2 dimensions, we get this memory, we can build a memory out of that. It's sort of obvious. But if you know more physics, this is not always the case. There's, the 1D Ising models and the phase transition, the 2D does. I mean, there are dimensionality constraints. And in these codes, you also see that. And I think that's fascinating and makes us understand when quantum information is stable, under what conditions it's stable. Now, of course, our goal is to make very stable quantum information and lots of it. And then we have applications. But as we all know, that's not going to happen tomorrow. So, and I don't think it contributes. This work doesn't directly contribute to that, right? Well, but of course, you never know how things contribute. Because if you look at the history of superconducting circuits, they weren't thinking about a 1,000 qubit machine when they observed the first coherence in a flux qubit or something.
Yeah, so you're looking at these properties of quantum information on driven by fundamental interest. But we know that that's how the future applications inevitably come about.
Right, this has been the story of the whole field, that you're just interested in the quantum Turing machine. But it has no, why not, right? So you never know.
Yeah, great. Yeah, that was all really interesting. Thanks for for presenting your work and joining us today. And thanks everyone for tuning in and asking questions and joining the discussion. So just start wrapping up. So next time we actually don't have a seminar happening next week, but we do. Well, the week after, on the 1st of December, I'll actually be giving the seminar instead of hosting, and that'll be on my work on quantum thermodynamics, looking at an exact form of irreversibility that's compatible with our reversible laws of quantum physics. So that's called Purifying the Demon. Does quantum erasure cost more than you remember? So I hope that you can join for that. And just before we finish, Barbara, do you have any final comments for our audience that have tuned in?
Oh, I don't know. Yeah, have fun doing science. Don't think too much about the applications.
That's
that
a great
advice.
Great. Yeah. So have fun doing science, everyone, and hope to see you at our future Qiskit events. So, bye for now.